Okay. So today I want to finish the discussion that we started last time on conformal quantum mechanics. And in particular, I want to explore a little bit the symmetries of conformal quantum mechanics. As I said, the theory is simple enough, rich enough that we're going to be able to learn a lot of the things that we want to learn, for example, about the conformal block structure of the theory, etc. Possible allusions to holographic dualities from this formal quantum mechanics. But for the moment, I just want to explore a little bit some of the basic structure of the theory. The basic structure of the theory is I want to talk about its symmetries, and in particular, we're going to explore a little bit of group theory or representation theory that underlie these symmetries. In particular, I will show you that SL2R, the formal group in 0.1 dimensions, is homomorphic to SO1.2, which is 2.1, which is the Lie algebra corresponding to three-dimensional Lorentz symmetry. So we'll say a little bit about how you make this identification, and then if there's time at the end of this lecture, I'll start the next section, which is a more formal description of conformal symmetries, which starts off with the simplest, more familiar conformal symmetry, which is Poincare. And then we'll build up from there. And by the end of today's lecture, by the end of Friday's lecture, we'll have enough material for me to give you the first exercise. So I'll upload that either on the weekend or next week, and then you have a week to work through it. But as you well know, these weeks can get time dilated, so depending on if you need extra time, I'll give it to you. Okay. All right, so conformal quantum mechanics is a conformal field theory in 0+1 dimensions, meaning all the dynamics takes place at a split single point in space, and the only variables in the problem depend on time. Right, so we're going to call the variable, the dynamical variable Q, and Q is going to be a function of T alone, and the Lagrangian for this theory in appropriate units consists of a kinetic term and a potential term, and the kinetic term is the usual half P dot squared. We expect kinetic energy minus G over 2Q squared, some normalization, and Q is a function T and T alone. Right, so as I said, it sounds very made up, but in fact, you can think of this theory as a particular dimensional reduction, 2+1 dimensional theory, where you take, let's say, a gas of electrons that are moving around in the plane, and you confine that gas of electrons to putting it into some really strong harmonic field to a single point in space, and you produce what's called a quantum dot. Right? The quantum dot all the way back in the 1990s. But at some extent, now there's still a lot of technology speaking. But you can produce dynamics that looks like this. So you can get this kind of dynamics from dimensional reduction. It's not really that made up. But it is a simple quantum mechanical theory. And as such, you might expect that it's solvable. And indeed, it is solvable. It's solvable classically and it's solvable mechanically. And it's solvable quantum mechanically. And the fact that it's solvable means that there's a lot we can learn from it. Okay? So we don't have to do numerical studies of this theory. We don't have to do asymptotic studies. We can get exact solutions for this thing. See what we can learn from those exact solutions and how much of those lessons are portable to the high dimensional cases that we really want to study. Okay. So In writing down this Lagrangian, I wrote down a Lagrangian like this specifically because it is time translation and scale invariant. Okay, so this is about construction. We ask, what can we do with 0 plus 1 dimensions to make a theory that is time translation invariant? Time translation invariant here is essentially Poincare between in 0 plus 1 dimensions. So we want something that's relativistic in 0 plus 1 dimensions, and we want it to be scalable. Okay. But then the next exercise you show that's okay. But by construction, this is scale and time translation. There. And I said last time that actually the theory that the symmetries that this theory exhibits is even bigger than this. In fact, I can change the coordinates, in this case as the time coordinates, by formal transformations and leave the theory invariant. So the Lagrangian one is actually invariant of the biggest symmetry, biggest set of symmetries, which we said T, so let's say T prime is AT plus B over C T plus D, where A, B, C, and D are all real parameters. And simultaneously, we then Q to Q prime, and Q prime is Q over C plus D. And the only constraint that I have is that A times B minus B times C must be 1. And then I said last time that I can take this set of transformations and I can code it in a matrix form. Right? So this and the represented and this word is key here, right? Represented is not, I'm not using the word likely. So whenever you have a transformation, a set of transformation in the form of group, if you can express those transformations in the group in terms of matrices, so we can bring linear algebra into the problem, then that's called a representation of the group transformations. It's not the only way of realizing transformations. You can realize that visually, you can realize that in other ways. In general, that's called a realization of the group. But when we talk about representation of the group, we talk about representation theory, we're talking about expressing things in terms of linear algebra. Okay. So this can be represented by the matrix, let's say A, which consists of the coefficient A, B, C, and D, and then the constraint that makes it into a symmetry is that AB minus BC is 1, but AB minus BC is the determinant of A. And so what we're looking for here are 2 by 2 matrices with real entries and unit determinant. Right? Instead of 2 by 2 matrices, so the group of informal and equals 1 space-time dimension. I use capital in general to denote space-time dimensions, and little g to denote just the spatial dimensions. It is the group SL to R. So the R here tells me that they're real entries of the matrices. The 2 here tells me that they're 2 by 2 matrices. The L here tells me that they're all linear maps. The S here tells me that the determinant is 1. Okay. And I'll let you do the next slide to show that the action of the variant underneath SL2R transformations. So I left off the last time by asking, what exactly do these conformal transformations do? Now, to answer this, we have to make note of the fact that the group SL2 R is homomorphic to the group of Lorentz transformations in 1 dimension, 2 dimension time. So let's start by noting that SL2R is homomorphic to SL you might wonder why I'm using lowercase here and uppercase here. I will in general use lowercase letters to denote the algebra of a particular Lie group. So the capital letters here will refer to the Lie group SL2R. The lowercase letters will refer to the Lie algebra associated to that Lie group. Now, just by way of a throwaway comment here, don't be lost. This might be more familiar. The words might be more familiar. Lie groups are spectral in the sense that every Lie group corresponds to, can be put into one-to-one correspondence to a differential map of space on which there's some differential calculus concept. And you can put into one-to-one correspondence to the group with that continuous space. Right. So then you also know that to each of these differentiable manifolds, I can define the same way that I can define for a curve or a general curve in 1 dimension. I can define a tangent to that curve. I can define a tangent plane as opposed to a tangent line to any point on this differentiable manifold. In particular, I can write down a tangent plane at the origin of the differentiable manifold corresponding to this SL2R or to any D. The thing that you should keep in mind is that when I talk about things living in that tangent plane, tangent plane is a vector space. So while they're generally abstract things living in this manifold, on the tangent plane, vectors live. They live in a vector space. Remember what I said, right? In general, there's some group structure which mathematicians love. But when I can represent this thing in a matrix, I can talk about linear algebra. When I talk about linear algebra, this is the kind of thing that physicists know, because you can bring all the linear algebra that we know to bear the problem. Okay? So the Lie algebra associated to a particular Lie group is nothing but the vector space that is the tangent space living at the origin of that. Okay, that's all it is if you want to think about geometry. So my notation here and going forward will be capital letters for the Lie group and lowercase letters for the algebra associated with that Lie. All right. So let me unpack this homomorphism. I'll tell you what I mean by this and how I can actually make this identification. So the first thing to note is that any group element of the Lie group SL2R, so any group element, anything that lives in this Lie group, right? Remember, we're talking about 2 by 2 matrices with real entries and unit determinant. It can be written in the form as follows. Any element of SL2R can be put into form, let's say G. G will take the form 1 plus A, B, C, and 1 plus BC over 1 plus A. Okay, and you can feel that the determinant of G by construction is 1. So what this means is that close to the origin, in other words, for small values, of the parameters A, B, C, and D, D takes the form 1 plus A, B, C, 1 minus A. Basically, I can just take a Taylor expansion using the fact that A is small and A times B times C is even smaller. Sorry, this solid. Okay. So the reason I want to do this is because from this form of what an element of SL2R looks like, I can immediately read off the generators of this approximation. I can read off basic matrices whose linear combinations I can take to produce a matrix that looks like that. Right? So the generators, we'll come back to word generators, the basic elements of the group or algebra that I can build all the other elements from. In this case, our matrix is X1, and X1 is going to be the matrix 1, 0, 0 minus 1. X2 is the matrix 0, 1, 0, 0, and X3 is the matrix 0, 1, 0, 0. And you can see that by taking combinations of linear combinations of those three matrices, I can build up any matrix like this. Of course, there's the identity as well, but we are talking about a group here, so taking that. Okay. All right. So let me do an example that's going to be, well, this example itself is not that important, but the set of such examples is important. We do a lot of these things in our course. Let's work out, given these three matrices, given these three generators of SL2R, let's work out what their commutation relations. The reason I want to work out what their commutation relations are is because commutation relations define what's called the algebra associated. From that algebra, I'll be able to read off what the associated B algebra that I'm telling you this thing is homomorphic to is. So we'll start off with this is particularly straightforward, right? So X1 commutator X2 is 0, 1, 0, 0 minus 1, 0, 1, 0, 0, minus 0, 1, 0, 0, times 1, 0, 0 minus 1, which is just 0, 1, 0, 0, plus 0, 1, 0, 0. It's 2 times 0, 1, 0, 0, but 0, 1, 0, 0 is just x2. Sorry. Okay. 2, 3. Yeah, sorry, it's just x2. So this is just 2 times x2. Right. Similarly, until the next one comes in with x3 is minus 2 times x3 itself. And x2 commutator x3 is just x1. So this is these three relations, these three commutation relations define the Lie algebra XL2R. So this corresponds to the Lie algebra SL. This is the algebra of SL capital S. So now let me ask you a question. How many of you know what the algebra for the Lorentz group looks like? How many have done any course, even like a first year course of carbon bio? So the algebra consists of the Poincare group consists of, as we spoke about last time, computations, rotations, and boosts. Right. So if you've seen MUs and computations with MUs and PMUs, you've seen where I'm going. Okay. If you haven't, we're going to talk about this in some detail in the next lecture. So that's it. And you're going to check all the algebra. Literally, yeah, unintended. You're going to check a lot of the algebra. Okay. But for now, again, if you've done any course with hyperpythons, then you almost certainly have seen this structure. But recall that the Lie algebra SO 2.1 is following MAB, MBC, MCB. This is theta BC, then AD minus theta BD MAC plus theta AD MBC minus theta AC MBD, and here A, B, C, and D take values 0, 1, 2. So we're talking about a two-state, one-time dimensional space-time. Okay. And eta is the diagonal matrix consisting of -1, +1, +1, and minus. So let's put this into a slightly more suggestive form. And to do that, I'm going to define T be the combination M02 minus M01. K is Qy the choice of letters a little later, M02 plus M01, and D to be M21. Okay. So again, A, B, C, and D take values 0, 1, and 2. So 3 by 3 matrix. Okay, it's not a 3 by 3 matrix. All the elements are independent. We put constraints on what their components can be. I'm taking 0, 2, 0, 1, combining them in 0, 2, minus 0, 1, 0, 2, plus 0, 1, and I'll call those something. And then I'll take 2, 1 entry and call it G. But then leave as an exercise you to show that in terms of these new operators, the new generators, that the SO over 1 algebra, that algebra takes the following form. If I calculate the commutator between D and P, I get this minus P. If I calculate the commutator between D and K, I get K. And the only other non-vanishing commutator is one between K and P. If I calculate that, that comes out to be 2D. And then up to some redefinition, this is nothing but the same algebra that we just worked out twice as well. Yeah, it's the sign supposed to be in the center. It's is a plus or minus. Yeah. It is. Don't fixate on that. It's just coding that particular relation. It doesn't really check those around as long as the signature product remains in this case plus one. So I'm going to come back to all of this in great detail in the next couple of lectures, where we construct the representation of the performance more generally. But I just want to make a couple of notes now to just finish off this particular section. In fact, I have enough time to start. So, the first point I would like to note is that to go from an algebra to the group, I have to exponentiate the generators. That's the standard procedure, and I've been doing that a lot. But in this 0 plus 1 dimensional setting, it's particularly simple. So the first point to note is that by exponentiating the infinitesimal generators, remember these are infinitesimal generators because we assumed that we were close to the identity, and A, B, and C, and D were all small, and we get Taylor expanded to that. So if I exponentiate these infinitesimal generators, I can write down the associated finite transformations. So by exponentiation, find the associated finite transformations. We will learn that P takes T, so that P takes T to T plus A, some constant A. D takes T to some constant P times T. And K takes T to T over 1 plus BT. So clearly, you can see that P corresponds to time translations. Just moving forward, shifting in time. Time translations. We say that P is the generator of time translations. Similarly, D scales by multiplying plus a number T. So this is scaling. We say that D is the generator of scaling transformations. Okay, in the context of the performance function that we're going to be exploring, it is what's called the dilatation generator. Yes.
Do they have a sign requirement on C? That we should be.
No, not yet. At this point, we don't have any additional requirements.
But in confirmation transformations, we need the.
Yes, in performance transformations, there will be additional constraints. And then K is a little bit more complicated. But what you can show, again, if you've done a course in complex analysis, you can show that this transformation that takes T to T over 1 plus BT is made up of a composition of inversions that take T to 1 over T, translations, and another inversion. Okay, so this is what's called a special performance transformation. As I mentioned at the beginning, so that's all I wanted to say about quantum mechanics for now. And as I mentioned in the beginning, this conformal quantum mechanics theory has the benefit that it is both simple and sufficiently rich that we're going to be able to learn quite a lot from it. But for now, I want to do this most formal exercise of working out things about the performance group. Give me 2 seconds. Because okay. So what I want to do now is work out the conformal group in all its gory details in generally D dimensions. Right. We've been working with the conformal group in 0+1 dimensions. That will equal 1. Incidentally, I can say that I'm going to be using capital D for the dilatation operator as well as for the number of space-time dimensions. It'll be clear from the context which I'm talking about. And if it's not, I'll make it explicitly clear when I'm talking. But our goal for the next 1 or 2 lectures is going to be to explore the conformal group in full detail in D dimensions. And our strategy is going to be the following. We're going to first explore the most familiar type of performance transformations to you, which is Poincare transformations. We're then going to add in scaling to that. And we're going to count all the constraints that come from this transformation. And then we're going to talk specifically about 2 dimensions, 2 spatial dimensions. Right? Because the formal transformation will be equals 2 are rather spatial. And a lot of what we learn in D equals 2 carries through to general D. The algebra gets a little bit tedious, but if we keep in mind what it is we did in D equals 2, then you can see where you're going with this. Right? So I will do a bunch of the calculations explicitly, and I will leave some place for you to fill in. Yes.
So, if we take small dimensions, then G will like to satisfy the determinant of G1, right?
Yeah.
So, doesn't that mean that one of C and D, one of these should have to be 0? Because we have entries like 1 plus A, 1 minus A, and so
yeah.
For small values, yeah.
Yeah.
So the determinant still has to be 1, right?
Yeah.
It's for a small value,
For small parameters. Yeah.
so the determinant here will be 1 minus BC.
It will be -square minus BC.
Yeah, so A square is given.
Yeah, but if A and B are if A and C are small, then AB and A squared are even smaller. So I disregard that relative to 1.
So we are also disregarding these.
Disregarding anything that's more 2. I'm taking A, B, C, and D to be all small. So if I multiply B times C, I'll get a smaller number relative to 1. Okay, so I want to start off then by just thinking about Lorentz about Poincare transformations, but a little more complex. So the section is going to be on performance entry. Our second was all about motivating why we're studying formal field theory. Okay. So let's start by looking at Poincare transformations. Poincare transformations are transformative transformations that leave the Minkowski metric invariant. Okay, what do I mean by this? So, under Poincare transformations in d dimensions, capital D dimensions, we're talking about transformations that take x mu, let's say x mu tilde, such that the Minkowski but I mean that I'm talking about R1 comma D, where D little d plus 1 is capital D. Such that the Minkowski line elements is invariant. Okay, let's explore what this means. So the Minkowski line elements R1 comma D is eta mu dx mu dx mu. It's taken generalized to a general forensic space time, but I will leave that exercise to you if you want to show how it happens. It's not too much more difficult. You know GR. And the point is that under this x mu to x mu total transformation, this thing goes to eta mu dx mu dx mu, where the x's are replaced by the x totals. And then I can use the chain rule to write these differentials as dx tilde mu by dx alpha, dx tilde mu by dx beta, dx alpha, dx beta. And if this is to leave, if this transformation is to leave the line element invariant, then I need this combination here to basically just be eta. So let's check the eta mu dx tilde mu by dx alpha dx tilde mu by dx beta must be eta alpha beta. I'm sure I explained this in my DG course, but if you weren't there or if you have done the course in let me explain the positioning of the indices here. An up index in denominator corresponds to a down index, right? And if I have repeated indices, then I will sum over those indices by max summation from them. Okay. Okay, so this is what we need. We need that eta mu and eta alpha beta are the same thing. So this is all well and good, but I'm trying to extract from this formula generators whose algebra I can calculate and from which I can figure out what transformation I'm talking about. Right? So to make sense of this, what for instance, we normally do is restrict ourselves to restrict our attention to infinitesimal transformations. Okay. Let's focus on infinitesimal transformations. And then once we have an idea of what we're doing there, we can always exponentiate generators and read off what the finite transformations are. So in and these transformations are from x mu going to x mu tilde and x mu tilde of order is going to be x mu plus some zeta mu. And where this side is small relative to this, and by which I mean component by component, small relative to this side, component by component. And so anything that's second order and these kinds of variables, I will drop relative to x mu. So let's take this and substitute this into here and see what we get. So substituting to 3. This means that eta mu d by dx alpha of x mu plus theta mu d by d beta d by dx beta of x mu plus theta mu is equal to beta mu delta mu alpha plus d zeta by d alpha. So that's going to be d alpha zeta mu times delta mu beta plus d beta zeta mu. Again, you're not familiar with the convention. D alpha means d by d alpha. D beta means d by d beta. Yeah. So contraction of eta with the delta tells me that I've got to replace, I match on the mu's and I replace it with an alpha. Right. And same with the beta, I contract on the mu's and replace it with a beta. So there's an eta alpha beta sitting there. And then there are terms, so this is going to be eta alpha beta plus d alpha zeta mu plus d beta zeta mu plus higher order terms. And all of this by equation 3 equal to eta alpha beta. And you can see that these two cancel out. The higher order terms we're discarding because they're higher order terms. So I don't care about these guys. And this tells me that equation 3 holds for infinitesimal transformations, provided d alpha zeta mu plus d beta zeta mu equals 0. Okay. This equation actually encodes for us the restriction of the symmetry that we need to obey. It is so important to carry the code name. It's called killing vector equation after killing. So the vector equation. In general, killing equations tell us about symmetry, about the symmetry that we're looking at. You'll find formal killing equations, etc. So the killing vector equation because it's a statement about these vectors, space-time vectors, etc. Yeah,
I think the indices are wrong. It should be alpha beta minus or plus beta alpha. Otherwise, you're gonna.
oh yeah, right. That is correct. If I forgot to correct. So this is the killing vector equation, and the killing vector equation encodes symmetries that we're talking about. So what we're going to do next time, what we're going to do next time is show how to solve the killing vector equation. Yeah, let's just do it. Alright, so let's see if we can solve the killing vector equation. So the first thing to know is that the killing vector equation is a first order differential equation for the vector zeta. Right. But it's written in a bit of a complicated way. What I'd like to do is write it in a way that will allow me to solve it. And the way to do that is to calculate to do the form of the second order differential equation. Okay, so we're going to differentiate this equation once and see what we can do. And I want you to pay attention, close attention to this particular game that we're going to play, because we're going to do it a number of times. Only the equations are going to get a little more complicated, but the game is going to be exactly the same. So let's take 4 and differentiate. And I'm going to differentiate with respect to let's say lambda. So if I differentiate, I'd say d lambda, and I don't really care what these indices are, but to be consistent with my notes because I'm going to be giving those to you. Let me change the alpha and beta to, let's say, sigma rho. D sigma beta rho plus d rho is equal to sigma. So we get 0. The form of the equation is to form 5. Then what I'm going to do is one parts equation, and I'm going to relabel the indices. I'm going to do it twice, and then take a linear combination of these guys to eliminate mixed derivatives. Okay, so similarly, the sigma of d lambda theta rho plus d rho theta lambda is equal to 0. And d rho d lambda theta sigma plus d sigma theta lambda is also equal to 0. All this 7. Okay. Each of these is now a second order differential equation. All I've done is differentiate this equation and play around with labeling a little bit. But here's what I'm going to do. I'm going to take the combination 5 minus 6 plus 7. 5 minus 6 plus 7 will give me that 2 times d lambda d sigma of zeta rho is equal to 0. Yeah.
Is this particular combination related to like S2 comma?
Yeah, no. It's now I'm just playing around with the transcript. It might be, but we're going to do much more complicated things in much higher dimensions. So general, general d dimension, I will still take a similar combination. In fact, I haven't told you anything about the number of dimensions. So we're now in d dimensions. So the performance we put in all the logarithms will be d dimension is a sort of d comma 1. Okay, but I'm still just taking this combination. But it's not physics. I have a differential equation. It's not a differential equation. Right now, explicitly in terms of the components, and I can designate those individual components. But we're sophisticated, and we know Greek, so we'll just do it once off, right? Point is, I now have a second order differential equation that looks like this. Okay, and it says that the second derivative of this vector zeta is 0. Okay, so what does that tell me about zeta? It is at most linear in x. Okay, so it must be a form a plus bx. All right, so when I take the first derivative of that, I get a, and when I take the second derivative of that, I get 0. So this means that zeta is at most linear in x community. In other words, that zeta mu say is a mu plus some omega mu x mu. Okay, this is how we write things covariant. So if I substitute this back into the first order form, I will find that it's only true. There's omega mu plus omega mu is equal to 0. With no other restrictions on A. So it doesn't have anything about A, the differentiated once A will go away, right? But it does put constraints on this omega. What it tells me is that omega is a matrix, okay, it's a capital D by capital D matrix, has to be an antisymmetric matrix. Omega an anti-symmetric D by D matrix. Okay. So let's take a step back and ask what this zeta is. Remember, we're talking about infinitesimal transformations. Those infinitesimal transformations are coded in zeta. So zeta is actually a vector of transformations for the Poincare group in d dimensions. Right? Now we've said all of this stuff only holds if zeta takes this particular form, right? And I can write it in terms of some constant vector and some antisymmetric tensor, technically, but matrix. Okay. So, what were we concerned about in the 0 plus 1 dimensional on mechanics? There, we were concerned about these x's, or in one case, the objects P, D, and K. These were the generators of the transformation. I use those generators to build up any transformation that I want, right? In the same group. So what I care about is the generators The question is, how many generators code for me the Poincare transformation into D dimensions? Okay, and it's actually sitting in how many parameters do I need to specify a beta. Okay, so let's say we're in D dimensions. So the question is, how many parameters? And the parameters are the independent numbers that I need to specify a particular zeta, right? So zeta must be written in this form. These are variables, so I don't get to play with this. But these guys contain the parameters from transformation. So how many such independent parameters do I need? Well, there's no constraint of A here. So if we're sitting in capital D dimensions, there are capital D numbers that go in here. With T of those guys. Okay, plus I have a D by D matrix, but not just any of the D by D matrix. I have a D by D anti-symmetric matrix. So how many numbers do you need to specify a D by D anti-symmetric matrix? Half D times D minus 1. Okay, because everything on the bottom triangle and off diagonal are constrained by what's sitting on the other side. So if I add these two things up, that's D plus a half D times D minus 1 is a half D times D plus independent parameters that specify infinitesimal operator in capital D. Which means that if I'm going to construct generators for these infinitesimal transformation, these are how many I'm looking for. Okay. All right. So now let's stop here today, and next time we will work out the generators and their Poincare operation.